on to part 4 of our space-time diagrams revisited. And so what we've done here is we've expanded our diagram from last time where we had Alice's plot, space-time diagram, her frame of reference, and then we figured out what Bob's space-time diagram, the axes, would look like if we put it also on the same plot as Alice's diagram. And this is what we got from last time. Note that, just to put some numbers here, we've chosen v equals 0.5 c for the relative velocity between the two frames of reference. Bob, in other words, is moving at velocity 0.5 c in the positive direction, which means gamma is 1.2. That will be important in a minute or two here. And we also mentioned last time that we had to be careful about the tick marks on the axes for Bob here. We can't just draw them in and assume they're in the same location because we have to go according to the Lorentz transformation equations. And we know that XA or XB and TB do not give us the same numbers in Alice's frame of reference, Bob to Alice or Alice to Bob here. So here's what we need to do. We need to say, okay, here's Bob's frame of reference in sort of standard form. And here are the points on his axes here. So for example, the point xb equals 0, tb equals 1 is this point right here. Okay, that's just on his tb axis. And this would be the point xb equals 0, t sub b equals 2, and so on and so forth. And the other points, this would be the point x sub b equals 1, t sub b equals 0, and so on and so forth. And so what we need to do is take each of the standard tick marks on Bob's frame of reference here in standard form and translate them, transform them using the Lorentz transformation equations onto the skewed axes here. We're not going to do all of them. We'll just do a couple examples so we can get the idea here, and then we're going to see what implications that has for how we can read things off the diagram. And in particular, we'll see that we'll be able to see time dilation and length contraction just from this diagram alone here, which of course makes sense because the whole thing really is based on the Lorentz transformation equation. So let's take a look at this. Bob's spacetime point, xb equals 0, tb equals 0. We're going to use the Lorentz transformation equations to figure out, we're going to be able to plot this point from Bob's frame of reference there onto Alice's plot here. And we expect it's going to appear on the t sub b axis, right? Because all these points are on the t sub b axis. In Bob's frame of reference, we showed that this is how the t sub b axis looks like when we put it on Alice's plot. And therefore, we know this point is going to be on here someplace. We just don't know exactly where. And that's what we need to figure out. So if we look at our equations up here, it's actually the top pair that work well this time. So we'll erase that and say, OK, because note I've got x sub b equals 0. So I can put 0 in for the x sub b's here. And t sub b equals 1. And so what I get for that, if I do that, so we're going to put these in here. So I get x sub a equals gamma. Now x sub b is simply 0 plus v times t sub b, which is 1. So I just get v times 1. And obviously 0 plus v is just v. So this becomes gamma v. And in fact, let's put some numbers in here for that. If gamma is 1.2 and v is 0.5 c here, 1.2 or really 0.5 c, and remember c is the speed of light, of course, and then we're using it in units of light years per year, so it just has the value 1 very nicely for us. So this becomes 0.5 times 1 and times 1.2, so 1/2 of 1.2 is 0.6. And this would be in units of light years or whatever we happen to, light type units we happen to be using there. So that gives us the x sub a coordinate of this point in Bob's reference frame, but transformed to Alice's. And then t sub a is simply going to be gamma times, now t sub b is 1 plus v over c squared times 0. In this case, x sub b is 0. And very simply, that just gives us gamma. And gamma is simply 1.2. Okay, so let's plot that now. So we say, okay, we found out that this point right here, that point there, from Bob's frame of reference, when I put it on Alice's plot, is going to appear at x sub a equals 0.6. So, you know, this is 1, 2, 3, 4. So it's about 0.6 is about right there. And t sub a is going to have a value of 1.2. So if we really move it up here, it's about right here is where it is. Now, when I'm putting tick marks on here, remember, tick marks need to be parallel to the appropriate axis. So all the tick marks here for t are appropriate to, or parallel to the x-axis, because really these represent many lines of simultaneity, right? These are all, this indicates, you know, all along there is a line of simultaneity for t sub a equals 1, t sub a equals 2, t sub a equals 3, and so on and so forth. And they need to be parallel to the x sub a axis in this case. So tick marks on the time axis need to be parallel to the xb axis. So here's the xb axis. Tick mark location, according to our results there, is that. So I don't know if I've got that quite right, but something like that. We'll draw it big there. Okay? So that is, that point right there appears right there, sort of in that blob there. Let's do another one, though. We won't do too many of these. Let's do one more here for the t sub b axis. So let's change this, not t sub b equals 1, but t sub b equals 2. In other words, now we're looking at that point. Where does that point occur on this axis? Okay, or on Alice's plot, really. And so we come up here. We can just very easily change our equation. Xb is still 0, so the zeros still are there, but the 1 just becomes a 2 here, and this one over here becomes a 2 for our second case. And we see we get 2 gamma v, 2 gamma v, and of course it's not going to be 0.6 anymore, so we get rid of that for a minute. And down here we get 2 gamma, 2 times gamma plus 0, so we got 2 gamma times v, 2 times gamma, 2.4 times 1/2, essentially, gives us 1.2. And 2 gamma is simply 2.4. So now we have another point. In other words, the point xb equals 0, t sub b equals 2, on Bob's plot over there for his frame of reference, transforms onto Alice's frame of reference into the point, okay, x sub a equals 1.2. So here's 1.2 approximately, and t sub a equals 2.4. So if we sort of go up here, roughly speaking, it looks like it's someplace right around there. Okay, so that's that tick mark. Again, this tick mark is parallel to the x sub b axis because it marks out lines of simultaneity there, as we were talking about in the last video clip. And we could continue doing this. We could do t sub b equals 3 and so on and so forth. And you can see the pattern here. We got one there. Well, next one will probably be, well, will be something like this, roughly speaking, and so on and so forth. Okay? So that gives us the tick marks on the TB axis. And now let's do the x sub b axis here. So in this case, we're looking for, let's do this point right here. We're assuming, by the way, the origins coincide. So the 0 point here matches up with the 0 point there, of course. But this is xb equals 1. So now we're looking at the point x sub b equals 1, t sub b equals 0. Okay, because now we're on the x sub b axis here. So xb equals 1, t sub b equals 0. What are the x sub a and t sub a coordinates in analysis plot for that? And so again, we have a situation here where just plug in the numbers. So these are the things that are going to be changing here. And we'll see what we get. Okay, so x sub a, gamma times x sub b. So x sub b is 1 this time. So there's a 1 here. And t sub b is 0. So that's very nice. We'll just put a 0 in there. And for this one, t sub b is 0. And we get a 1 over here. So the top one is just gamma times 1 plus 0. So this just becomes gamma. And the bottom one becomes 0 plus v over c squared times 1. So it's gamma times v over c squared. And putting some numbers in here from before, gamma is 1.2. Gamma is 1.2. And c squared is going to be 1 for our units of light years per year. So I've got gamma times v, and that's going to be 0.6. 0.6. So now we have this point right here, is what we're working on now, and that one's going to come over here in Alice's coordinates to xa equals 1.2, so about right there, and t sub a equals 0.6. So up here like this, about right there. I'm a little off in my plot here. But so that's the location, and the tick mark now is going to be parallel to the TB axis. So it's, again, roughly speaking, you want to draw something like that. Maybe a little off there. Try not to make it too big, but that's what that tick mark looks like. Okay, let's do one more here. So xb equals 2, because then we'll see the pattern. xb equals 2. So now we're looking at this point right here on the x sub b axis. T sub b is 0. And so we come up here. The zeros stay the same. This becomes a 2. This becomes a 2. And we get 2 gamma and 2 gamma v over c squared in those cases. So we get 2.4 and 1.2. 2.4, 1.2. And so we go x sub a equals 2.4. So over to about right here. And 1.2, so we're about right there. And we try to draw it roughly parallel to that. And then we get other results as we go along. So the next one would be something like about right here probably, and so on and so forth. Okay. Now, what that means here is there are lines of simultaneity and lines of same location in terms of Bob's axes here. And so again, they're parallel to the t sub b axis, so they would be roughly like that, like that, like that. Okay, and extending down too, of course. All the way down there. Okay, and then the line. So those are lines of same location. Hope I said that right. Lines of same location here for a given value of x sub b. So this is 3. This is 3 light years on the x sub b axis right there. And anywhere on this line here, as far as Bob concerned, those would be events that happen at 3 light years for any given time. And then the lines of simultaneity for Bob on this plot are parallel to the x sub b axis. So it sort of looks like this. Try to get it in here. And of course, it goes the other direction too. Okay, hopefully you get the idea there. This is really something you need graph paper for to get it looking right. Okay, so now let's see what we can get out of this result here. Let's look at a case where we have a certain point, a certain space-time event. And let's focus on Alice's coordinates here for a minute. And let's do her a few lines of simultaneity in same location. So lines of simultaneity here, sort of there, like that. I don't want to make it too messed up here. Something like that. So I can see it's getting a little messy there. But let's see if we can see what's going on here. So what this means is anywhere along this more or less black straight line here, that's a line of simultaneity for Alice. That's t sub a equals 1. Okay? So let's see where that intersects with Bob's t sub b axis, in particular right here. Right there. If that space-time event occurred, a flash of light say, Alice would measure it at t sub a equals 1. Okay? Right there. And her x sub a would be maybe 0.4 or something like that down here. Okay, so that would be, for Alice, it would be x sub a equals 0.4, t sub a equals 1. Okay, that would be the flash of light, and her coordinates for the flash of light. Look at what Bob's coordinates are for the flash of light. Okay, so let's figure that out. So for this flash of light for Bob, clearly it's happening on his time axis, so that's x sub b equals 0 for him. Okay, it's happening right where he is, so it'd be xb equals 0, okay? Because the t sub b axis is, by definition, x sub b equals 0, his location. And what's the time for him? The time for him is, well, note where the t sub b equals 1 point is. It's right here. It's right there. And that's less, the flashlight is occurring less than that time. It looks like, from here to here is 1 for one light, not 1 light year, 1 year for Bob, from there to there, tick mark of 1. And therefore, maybe it looks like about 0.7, just roughly speaking, maybe 0.75, someplace in that region. So we'd say TA, just very roughly here, we're trying to get a rough idea, 0.7, 0.8, someplace in that vicinity, just trying to read it off our somewhat imprecise graph there. But it's precise enough to see that clearly when Alice measures that event at 1 year on her clock, here's synchronized clocks, Bob, his clock reads 0.7. Oops, sorry, this is not A here, B. Bob's clock is 0.7. What do we have there? That's time dilation. Alice sees Bob's clock running slowly, then more slowly than her clock. Okay? So, and we could do a precise, obviously, it's going to be a 1.2 factor here, we know from earlier results. And so I don't know if, 1 divided by 1.2, it's probably not quite 0.7, but it's in the vicinity there. So that's time dilation that we can see out here as well. And it's a little harder to see on this plot, but you can also see length contraction, okay, because a given length is going to be shorter to Alice than to Bob. So let's see if we can just get a feel for that. You see that a given length, right, is going to be shorter for Alice compared to Bob. The proper length in Bob's frame of reference, say for his spaceship. So let's look at this and see that, well, what is length here? Let's say just this distance here, right there, is a standard length of 1 to Alice, right? Okay. A standard length of 1 to Bob is this vertical line here on this plot. Okay. Clearly, this line is longer than that line. Okay. So in other words, if Alice is comparing 2 points, say the beginning and end of Bob's spaceship, she'll get a shorter value, a shorter measure of that than Bob will. And it's a little messy there, not quite so precise, but hopefully you get the idea that this actually shows not only time dilation, it shows length contraction as well. And in fact, one other thing you can see here, and we'll do this in the next video clip, is you can see the relativity of simultaneity and leading clocks lags. That's what we'll work on next. Okay, now part 5 of our revisit to space-time diagrams. We've tried to clean up our diagram from last time just a little bit. So let's review what we've got here. We've got Alice's plot, her frame of reference, the XA axis, the T sub A axis in normal right angle configuration. And over the last couple of video clips, we've shown that we can put Bob's frame of reference on the same plot if we draw the X sub B axis at an angle like this and the T sub B axis at an angle like that. And of course, we figured out what the angles have to be. Remember, the T sub B axis in particular is Bob's world line. He's sitting in his rocket ship, traveling velocity v. Alice is observing from his perspective. He's just sitting at X sub B equals 0, which is the T sub B axis here. To do the exact transformations, of course, we can use our transformation equations here, but the plot gives us some insights just diagrammatically or pictorially of things like time dilation and length contraction. We tried to point that out a little bit last time. And this time we want to point out that relativity of simultaneity is very evident from the plot as well. But again, let's orient ourselves so that, note for Alice's plot, we have lines of simultaneity. T sub A equals 1 is this line. We'll get to the red dots here in a second. T sub A equals 1, T sub A equals 2, T sub A equals 3, and so on and so forth. We did not draw lines of same location for Alice just because it gets to be a little much on here, but they would be, x sub A equals 1, x sub A equals 2, x sub A equals 3, and so on and so forth like that. Now, what about Bob's plot? We have the T sub B axis at an angle here, and the x sub B axis at an angle this way. And note, in particular, we've got lines of simultaneity for Bob on here. Those are the lines that, just like Alice's lines of simultaneity, are parallel to her x sub A axis, because this is really T sub A equals 0 here. Bob's lines of simultaneity are parallel to his x sub B axis. And so the x sub B axis is essentially T sub B equals 0. The time he measures is 0. Then we've got the T sub B equals 1 line, 1 light year if we're using light years, and C is light years per year, 1 light year per year here. T sub B equals 1 is this line. T sub B equals 2 is this line. T sub B equals 3 is this line. And as much as possible in our diagram, remember, we've actually figured out exactly what the spacing is between those lines of simultaneity for the T sub B's, and similarly for the lines of same location, x sub B equals 1, x sub B equals 2, x sub B equals 3. Now, in certain places, my diagram's slightly off there, but hopefully you can see what's going on with that. So, now let's get to the point here, is that let's say that these red dots are flashes of light. Let's do Alice's perspective. Flashes of light. We're actually going to look at the T sub A equal 2 line of simultaneity. So if all I told you these were flashes of light, maybe flash photographs that Alice is taking in her frame of reference, note, as far as she's concerned, they're all simultaneous. They all occur at T sub A equals 2 years if we're doing light years per year for C, or 2 seconds if we're doing light seconds per second. So they all occur at T sub A equals 2. Again, we know that Alice has her line of synchronized clocks. Bob has his line or lattice of synchronized clocks as well. So in Alice's frame of reference, she shoots off flash photographs on her line of synchronized clocks at T sub A equals 2. And those are specific, unique space-time events at each of those locations. And in her frame of reference, they all occur at T sub A equals 2, and I've drawn them so they occur at like x sub A equals 0, x sub A equals 1, 2, 3, 4. So we'll assume she just has clocks at those locations, and they're synchronized for her. Let's see what the diagram shows us in terms of Bob's perspective on this line of flash photographs that have gone off. Well, let's start with this one right here. And actually, before we get into that, let's situate ourselves. Remember, Bob is moving to the right, positive x direction. From Alice's perspective, from his perspective, he sees Alice going in the other direction. Okay, so if these were clocks in Alice's frame of reference, she's taking flash photographs of, Bob, from his cockpit, would see them going this way. They're going to the left. In Alice's frame of reference, they're stationary. They're -1, 0, 1, the lines of same location. They're not moving. In Bob's frame of reference, they're moving to the left. Okay, so let's start with this clock right here, that flash photograph of Alice. And we can see that it's on the x sub B axis. Okay, so that's T sub B equals 0. So to Bob, that flash would occur at T sub B equals 0. The next flash here is on a different line of simultaneity for Bob. It's at about 1/2 maybe. T sub B, so you have to imagine these lines of simultaneity for Bob parallel to the x sub B axis. So this is another time line, as it were, and that's maybe at T sub B equals 1/2 there. Okay, and then this third flash here occurs maybe just past T sub B equals 1 there. Fourth flash occurs at maybe about 1.7, 1.8 to Bob, and this flash just past the TB equals 2 line of simultaneity, and then this flash here maybe, I don't know, about 2.7, something like that, just under TB equals 3. So to reiterate, what we're saying here is that Bob observes this flash to occur at TB equals 0, this one maybe about 1/2 second or year, depending on the units we're using. This at about 1, maybe about 1.7, 2.1, 2.7, something like that. Okay? If we wanted to get exact numbers out of this, remember we could use the Lorentz transformation equations. In other words, Alice says, okay, I've got flashes of light at t sub a equals 2 and x equals 1, 2, 3, 4, and 5 and 6 or whatever. We could take those values, plug in Alice's xa and t sub a values for each of those flashes, and get the xb and tb values that Bob sees. Okay? But the diagram shows us more pictorially what's going on. But if we wanted the exact values, we could get them from the equations. In fact, of course, we built this using the Lorentz transformation equations. So what's the conclusion here? The conclusion is clearly we have relativity of simultaneity. That clocks that are synchronized in one frame of reference, Alice's frame of reference, are not synchronized in Bob's frame of reference. In other words, he sees this clock go flash first, and then this clock, and this clock, this clock, this clock, and this clock, in that order. Okay? Now to Alice, remember, all those clocks are synchronized. So when the flashes go off, she will see the same time. The flash photograph will show the same time on each of those. But Bob sees the flashes occur at different times, not the same time. So let's just say, well, let's not just say, it is right here. All the times shown on those flash photographs are t sub a equals 2. 2 years, okay, on those clocks. Bob will say, okay, on the first clock, that one happened at t sub b equals 0. 0 years. This one happened about 1/2 year. This at about 1.1, 1.8, and so on and so forth. And note another thing about this. So first of all, relativity of simultaneity. Bob is saying, Alice, your clocks are all messed up. You may think they're synchronized, but clearly I see them as unsynchronized. These flashes are occurring at different times, and even though the times in the photograph show that your clocks are reading the same time when the flashes occur, the flashes are clearly not occurring at the same time, which means your clocks are not synchronized. In other words, what Bob is saying really is, in my frame of reference, your clocks are not synchronized. Where Alice is saying, well, clearly they're synchronized, but that's in her frame of reference. The other thing we can get out of this, qualitatively, is leading clocks lag. Because think about this a minute. Here's this line of clocks, and Bob is seeing them flash one after the other. This one, then this one, then this one, then this one, slowly, of course. And again, these clocks are heading leftward compared to Bob. And since we know when they flash, they all read the same time. So when this one flashes, it reads 2. When 2 years, 2 years, 2 years, 2 years, 2 years, 2 years. So to Bob, this one flashes first and reads 2 years. This one flashes last and it reads 2 years. What is the leading clock from Bob's perspective? This is the leading clock here. It's moving in this direction. So as he's observing Alice's clocks go by, this series of clocks, this is the leading clock. It flashes last and reads 2 years. This one flashes first and reads 2 years. This clock is definitely behind that clock by a given amount that we could actually figure out from the diagram or the Lorentz transformation equations, or simply by our dv over c squared equation we got when we did a quantitative analysis of leading clocks lag. But again, space-time diagram like this now, where we can put both frames of reference on the same plot, allow us to analyze things without necessarily going into the details of the equations, because again, this is built on the equations. And we see here that, yes, we see relativity of simultaneity, and we see leading clocks lag. So this is one of those things. Ponder a little bit. It's useful even to construct your own. Get out some graph paper if you have some, and work through essentially the exercise we did the last couple of video clips to construct this. And then just sort of plot various things on there. See if you can figure out what's going on from Alice's perspective versus Bob's perspective.